Section: Introduction. In this section, we discuss recent advancements in large language models, LLMs, that have made AI agents effective for complex tasks like search and code generation. These agents show great flexibility by using LLMs to adapt to various tasks. However, despite improvements through prompt engineering, LLMs still have significant limitations, particularly when faced with tasks they weren't specifically trained for, such as multi-turn coding or unfamiliar tools. This highlights the need for training or fine-tuning models within agents to fully harness LLM's potential in real-world applications. We recognize that training models in real-world scenarios is essential for enhancing model capabilities. During agent execution, we generate valuable interaction data that reflects the complexities of real-world problem-solving, which is more diverse and extensive than traditional datasets. Utilizing this data for fine-tuning not only sharpens an agent's skills but also helps develop more adaptable LLMs for dynamic environments. Reinforcement learning, RL, has been pivotal in advancing reasoning models and offers a strong framework for optimizing LLMs in agent scenarios. Unlike supervised learning, which requires detailed annotations, RL uses outcome-based rewards, allowing agents to learn from feedback without needing curated data. This trial-and-error approach mirrors human learning, enabling models to develop action strategies based on real-world contexts. However, applying RL to agents presents challenges in algorithm design and implementation. Current RL methods are mainly designed for static tasks, while agents require handling multiple LLM calls and interactions with various tools. This complexity and the need for tailored agents for different applications complicate large-scale LLM tuning. To address these challenges, we introduce Agent Lightning, a flexible framework that facilitates RL-based training of LLMs for any AI agent. Agent Lightning separates agent execution from RL training, allowing developers to train existing agents with minimal code changes. We frame agent execution as a Markov decision process, where the state reflects the current execution status, and the action is the output from the policy LLM that updates the state. We propose a unified data interface for RL training, structuring agent trajectories as sequences of transitions that include the current state, action, and reward. This interface simplifies the underlying orchestration, making it applicable to any agent. To optimize the policy LLM using these transitions, we introduce Lightning RL, a hierarchical RL algorithm designed for agent training. This method allows for flexible context construction and simultaneous optimization of multiple agents while addressing the issue of long sequences. Agent Lightning also features a training agent disaggregation architecture, consisting of a Lightning server and Lightning client. The server manages the RL training process and provides an API for the updated model, while the client handles communication and runs the agent for data collection. This setup connects observability frameworks to the training process, enhancing scalability and flexibility. We also implement an automatic intermediate rewarding mechanism to address sparse rewards by assigning intermediate rewards based on system monitoring signals. This customization helps improve training effectiveness. We demonstrate Agent Lightning's effectiveness through various tasks, including a text-to-SQL agent and a math question answering agent. The results show that Agent Lightning leads to continuous performance improvements across different scenarios, indicating its potential for real-world applications. In summary, Agent Lightning represents a significant advancement in agent training by fully decoupling agents from RL training, allowing for seamless application to any AI agent with minimal code changes. This alignment with agent execution logic enhances performance in real-world tasks and enables the collection of diverse data to improve model capabilities. Through specialized algorithm and infrastructure designs, we achieve efficient training and a clean separation between RL training and agent execution, ensuring extensibility and integration with various agent frameworks. Section Summary. In this section, we discuss the limitations of large language models, LLMs, in complex real-world tasks and introduce Agent Lightning, a framework that decouples agent execution from reinforcement learning, RL, training, allowing for seamless integration with any AI agent. By leveraging a unified data interface and a hierarchical RL algorithm, we enhance agent performance and adaptability while addressing challenges like sparse rewards and the need for diverse training data. Section: Modern AI Agents. In this section, we discuss modern AI agents, which are difficult to define due to their variety and rapid changes. While many have tried to categorize them, we aim to provide a broad understanding. An AI agent is a software system that uses one or more calls to large language models, LLMs, during its operation. This definition includes a wide range of AI agents, from those that follow set workflows to more advanced multi-agent systems that can plan, reason, and operate over longer periods. We identify two main components for building agents. First, LLMs, or foundational models, act as the primary engines for reasoning and generating responses. Each generation from an LLM is a direct transformation from an input prompt to an output response. Due to their high computational needs, LLMs usually run on powerful servers or cloud services, accessed by agents through API endpoints, whether from commercial providers or self-hosted solutions. An agent can utilize multiple LLMs, each with a unique endpoint, to perform various tasks. We denote the set of LLMs used by an agent as a collection of models, where each model can have different versions and parameters. Second, tools are specific functions that agents use to carry out tasks, like fetching data from a database or executing code. These tools can either maintain context between uses or not, and they can be implemented in various ways, such as through external APIs or local programs. Recently, many tools have adopted standardized communication protocols to ensure smooth interactions with agents. For orchestration, we use the combined set of LLMs and tools as building blocks. The execution flow and order of these components are typically tailored by the user based on the task at hand. This orchestration is often flexible and can change dynamically. For example, an LLM might decide whether to refine a query or provide an answer directly, leading to varying interactions with a database. In game-playing scenarios, the agent's actions and feedback from the environment are represented as a series of LLM calls, where each call corresponds to a decision point. This dynamic interaction can enhance task-specific behaviors but also complicates data modeling and learning, making it challenging to implement different agents using current reinforcement learning frameworks. When it comes to implementation, developers have various options for creating AI agents. Some may build agents from the ground up for full control, while others might use established frameworks that speed up development. These frameworks offer modular components and flexible orchestration methods, allowing users to create workflows that adapt to task needs and the agent's state. However, whether built from scratch or using frameworks, agents often lack automatic self-improvement mechanisms and optimization processes. In practice, especially with private data, agents frequently do not meet performance expectations, highlighting the need for automated optimization. We then introduce our Agent Lightning framework. We start by defining a unified data interface that outlines the data collected during agent execution, independent of the agent's design. Next, we explain the Markov decision process in agents, which lays the groundwork for reinforcement learning. Following that, we present our hierarchical reinforcement learning algorithm that uses the collected data to update the LLM. Finally, we describe our specialized infrastructure, which includes several design features that greatly simplify the agent training process. Section Summary. In this section, we provide an overview of modern AI agents, defining them as software systems that utilize one or more LLM calls, and discuss their components, orchestration, and development frameworks. We also highlight the challenges of dynamic behavior in agents and introduce our Agent Lightning framework, which aims to enhance agent performance through automated optimization and reinforcement learning. Section: Unified Data Interface. In this section, we define a unified data interface that is crucial for optimizing data-driven agents during their execution. This interface outlines how the data generated by agents is utilized in reinforcement learning (RL) training algorithms. It is designed to be general enough to work with data from any AI agent, which we view as a type of software that can be represented as a directed acyclic graph, DAG. In this graph, each node represents a component call, either from a language model or a tool, while the edges show the dependencies between these components. We found that reconstructing a complete graph from messy execution traces is complex and not necessary for training. Instead, we can focus on the current state of the agent and the main factors that influence transitions between states, which are the calls made during execution. We define the state as a snapshot of the agent's execution, including elements like the program counter, variable values, and the call stack. This state evolves over time, and the same task can yield different execution traces due to the agent's dynamic behavior. We emphasize key variables, which we call semantic variables, that are crucial for understanding the agent's intent. These variables change through component invocations. For each execution of a task, we track the component calls, where each call includes the component being invoked, the input and output data, and relevant metadata about the invocation. To facilitate learning from the data collected during execution, we introduce reward signals that measure the quality of task completion. Each execution is paired with scalar rewards that correspond to the quality of each invocation. Rewards can be given at various points during execution, providing feedback that helps guide the agent's learning. In many cases, we may only have a final reward to assess the overall success of the execution. To illustrate our approach, we consider a Retrieve Augmented Generation (RAG) agent that answers user queries by first retrieving relevant documents and then generating a response based on those documents. This agent consists of a generative model and a search tool. The execution process involves the user inputting a question, the agent generating a search query, retrieving relevant passages, and finally producing an answer. Each state during execution captures the current values of the semantic variables, and as the agent makes calls, these variables are updated, leading to new states. Our unified data interface captures all changes in state, allowing for flexible optimization methods. It supports selective optimization of specific agents and extends beyond just fine-tuning models. While our focus is on optimizing language models, the versatility of our approach is evident. By documenting the complete execution context in each state, we enable effective policy learning and simplify RL-based optimization for various agent workflows without needing to parse the entire execution graph. Section Summary. In this section, we define a unified data interface in Agent Lightning that streamlines the integration of data generated during agent execution into reinforcement learning (RL) training, focusing on key variables called semantic variables that capture essential state information. This approach simplifies RL optimization by allowing us to leverage state transitions without the need to parse complex execution graphs, thus facilitating flexible and customizable agent training across various workflows. Section: Markov Decision Process in Agents. In this section, we explore the Markov Decision Process, MDP, as it applies to agents. We start with a straightforward example: an agent that uses a single large language model, LLM, for optimization. By viewing this LLM as a policy model, we can represent its decision-making as a partially observable Markov decision process, POMDP. We define the POMDP using a tuple that includes the state space, which encompasses all possible states, the observation space, which includes all potential inputs to the LLM, the action space, where each action is the complete sequence of tokens produced by the LLM in one call, the transition dynamics, which describe how the agent moves to a new state, and the reward function, which assigns rewards based on state-action pairs. At each time step, we have a snapshot of the agent state and the LLM observes a context that is necessary for decision-making. The LLM then generates a sequence of tokens as its output, treated as a single action. After executing this action, the agent moves to a new state, and a reward is given to assess the action's quality. Our goal is to maximize the total rewards over time. For reinforcement learning, RL, we need to gather data that includes all decisions made by the LLM and their corresponding rewards. We extract relevant information from each execution, focusing on the raw input, the LLM's output, and the rewards. The LLM calls are flexible and can handle various types of information, such as instructions, conversation history, and user queries. This allows us to streamline the RL training process by concentrating on the current input and output, avoiding the complexities of the underlying logic. In summary, our unified data interface and MDP formulation enable us to separate the design of task-specific agents from the learning-based optimization of policies, facilitating effective RL in dynamic agent systems. We also note that this formulation can easily adapt to multi-agent scenarios using a single LLM, where the model can perform different roles based on the prompts. For instance, in a retrieval augmented generation (RAG) scenario, the LLM can first generate a search query, which updates the state, and then provide an answer to a question, with the quality of that answer determining the reward. This flexibility allows a single LLM to function as multiple agents, and our framework supports optimizing specific agents within a multi-agent system by including their transitions in the optimization process, making it more intuitive than traditional masking methods. Section Summary. In this section, we formulate the decision-making process of an agent with a single LLM as a partially observable Markov decision process, POMDP, where the LLM's actions and rewards are used to optimize its policy through reinforcement learning. We also demonstrate how this framework can be applied to multi-agent scenarios, allowing a single LLM to perform different roles and optimize specific agents within a system efficiently. Section. Extension to multi-LLM setting. In this section, we extend our discussion to the scenario involving multiple distinct large language models, LLMs, that need to be optimized together. A simple method is to treat each LLM as an independent decision-making process and optimize them separately. While this makes training easier, it overlooks the relationships between the models, which can lead to poor coordination. A better approach would be to use multi-agent reinforcement learning or game theory, where each LLM is seen as an agent with its own goals and strategies. This method captures the interactions and behaviors, whether competitive or cooperative, between the LLMs more effectively. We also look at recent developments in reinforcement learning, RL, for LLMs, particularly focusing on single-call tasks where the model generates a response in one go. These techniques are mainly used in areas like math and logic problems. In this context, when given a task, an LLM produces a response token by token, with each token considered an action. After generating the full response, we assign a reward based on how correct or high quality the solution is, comparing it to the true answer for the task. The loss at the token level can be simplified, focusing on how we estimate the advantage of each token. Traditional methods like proximal policy optimization, PPO, use a learned model to define this advantage, while newer methods aim to simplify training by removing the need for a separate value function. To address the limitations of existing methods, we introduce Lightning RL, a hierarchical reinforcement learning approach that works well with current single-turn RL methods for LLMs. This approach allows us to treat the entire sequence of tokens generated in one LLM call as a single action, while still enabling multiple actions through interactions to complete a task. Lightning RL organizes data into transitions, each containing the input, output, and reward for a specific LLM call. It uses a two-step process. First, it assigns a return across actions, and then it breaks this down into token-level signals. In our current setup, we assume that all actions in an episode have the same value, which is the final return. This design has several benefits. It allows us to use any single-turn RL algorithm without changes, particularly lightweight methods. For instance, we can group samples from the same task to estimate advantages, similar to how we do in GRPO. Additionally, Lightning RL provides flexibility in how we construct observations, as our data is organized at the transition level. This means we can derive current inputs from various sources, such as summaries of previous steps or structured prompts, unlike previous methods that required concatenating all turns into one response. Moreover, Lightning RL offers a more robust and scalable solution compared to masking strategies, which complicate the training and execution processes. By breaking down agent trajectories into transitions, we align better with the LLM's input structure and avoid the complexities introduced by masking. This approach simplifies implementation and enhances scalability, allowing us to manage long contexts more effectively by using batches of transitions for updates. Section Summary. In this section, we explore the optimization of multiple distinct LLMs using multi-agent reinforcement learning, MARL, to better capture their interactions, as opposed to treating them as independent entities. We also introduce Lightning RL, a hierarchical reinforcement learning approach that integrates seamlessly with existing single-turn RL methods, allowing for flexible policy observations and simplifying the implementation by organizing data into transitions without the complexities of masking. Section: More Sophisticated Credit Assignment. In this section, we discuss the more advanced credit assignment methods. Our credit assignment module is designed to support the integration of more sophisticated strategies, such as assigning credit based on heuristics or learned models. One promising direction for future research is to introduce a high-level value function that estimates the expected return for each action individually, which would allow for a more detailed distribution of credit. However, our experiments show that a simple identical assignment strategy works well across various scenarios and datasets. Next, we address the system design of Agent Lightning. Training large language models, LLMs, for real-world agents is quite challenging due to the need to combine reinforcement learning, RL, training frameworks with agent development frameworks. These frameworks can be complex and rapidly changing, making alignment difficult. The Agent Lightning framework provides a unified solution that simplifies the development and training of agents using RL and other optimization methods. We then describe the training agent disaggregation architecture. This RL training framework for LLMs has two main parts: the trainer, which updates model weights, and the rollout, which captures data trajectories for the trainer. For single-turn RL tasks, like mathematical reasoning, the rollout is straightforward, involving just the generation of LLM responses to specific prompts. In contrast, for multi-turn tasks that require interaction with environments, the rollout must fully execute agents, including generating multiple LLM responses and running native code. The key innovation of Agent Lightning is its architecture that separates the resource-intensive LLM generation from the lightweight application logic and tools, which are written in traditional programming languages. The RL framework manages the LLM generation and provides an API for the application logic, allowing them to operate independently and enhancing flexibility in defining agent behaviors. We also highlight the benefits of agent-agnostic training and trainer-agnostic agents. Our architecture creates independence between the training framework and the agent, making the training framework agent-agnostic, focused solely on optimizing the LLM and managing hardware resources. Meanwhile, the agent operates independently of the training framework, allowing developers to focus on agent logic without being constrained by the training infrastructure. We provide a code example in the appendix to illustrate how easily an existing agent can be optimized using Agent Lightning. To achieve our design goals, we introduce a two-component architecture: the Agent Lightning server and the Agent Lightning client. The server integrates with RL frameworks, managing training and LLM optimization, while the client allows agents to function independently of the training framework. When a user uploads a task dataset, the server orchestrates the training process, dividing the dataset into batches and managing transitions between generation and training stages. It dispatches task batches to clients and provides a unique API endpoint for each task, enabling data tracing and capture. The client executes agents to generate traces and rewards, which are sent back to the server for processing and model updates. This architecture supports efficient and scalable agent training by leveraging the strengths of both the RL and agent development frameworks. Finally, we describe the agent runtime. The Agent Lightning client acts as a runtime manager for agents, coordinating execution, capturing data, handling errors, and communicating with the server. It ensures that the agent training workflow is robust, scalable, and efficient. We also emphasize the importance of data parallelism for agent execution. Large batch sizes are crucial in modern RL training to optimize computational resources and reduce rollout latency. To handle these large batches, multiple agent instances must run in parallel. The Agent Lightning client is designed to manage and execute multiple agent instances concurrently, using a two-level parallelism strategy: intranode parallelism, where one client runs multiple workers on a single machine, and internode parallelism, where multiple clients operate on different machines. This setup allows for flexible scaling and efficient resource use across distributed systems. Section Summary. In this section, we discuss the Agent Lightning framework, which integrates reinforcement learning, RL, and agent development to streamline the training of large language models, LLMs, through a disaggregated architecture that separates model training from agent logic. We highlight the framework's flexibility, allowing for agent-agnostic training and efficient execution of multiple agent instances in parallel, ultimately enhancing scalability and resource utilization. Section: Data capture without code modification. In this section, we discuss how we capture data without modifying existing agent code. The Lightning client uses two techniques for this purpose. The first technique leverages tracing capabilities to automatically gather execution traces, LLM calls, and environment interactions. For those who prefer not to use this method, we offer a simpler tracing mechanism within the OpenAI-like API endpoint, which is efficient and scalable for various agent development frameworks. Next, we address error handling and robustness. We recognize that the training process must be stable and reliable, especially during long sessions where failures can occur due to crashes, network issues, or invalid outputs. These errors are more frequent in reinforcement learning, RL, training compared to inference. To mitigate downtime and resource waste, our client includes robust error handling that detects unaddressed failures, allowing us to retry or reassign tasks while maintaining detailed logs for monitoring and debugging. We also introduce automatic intermediate rewarding, AIR, to tackle the challenges posed by delayed and sparse rewards in RL training. By providing feedback at different stages of agent execution, intermediate rewards enhance learning without the high overhead of human annotation or complex computations. Our AIR mechanisms convert system monitoring data into these rewards, improving the training framework's effectiveness. For scalability, we recognize the importance of environments and reward functions in RL training. Lightweight environments can run locally with the agent, while resource-intensive ones are better hosted as shared services. Currently, our client supports simple pooling for these services, with plans to expand to more complex serverless architectures in the future. We validate the effectiveness of Agent Lightning across 3 distinct tasks, each using a different agent framework. The results demonstrate continuous and stable performance improvements, showcasing its potential for real-world agent optimization. In the text-to-SQL task, we require the agent to generate SQL queries from natural language questions using the Spider dataset, which includes over 10,000 questions across various databases. We utilize the LLAMA 3.2 to 3b instruct model in a multi-agent system with 3 agents. The SQL writer generates a query, which is executed, and the SQL executor returns results or error messages. A checking agent evaluates the query's correctness and the retrieved information, deciding whether to rewrite the query or generate an answer. The rewriting agent then revises the query based on feedback or answers the question directly. During training, we optimize the SQL writing and rewriting agents simultaneously, demonstrating that Agent Lightning can selectively enhance agents within a multi-agent system. This task requires the LLM to generate valid SQL queries, check their quality, and ultimately provide accurate answers. The reward is based on the correctness of the final answer, and we evaluate the model's performance on the test set. Our findings show that Agent Lightning facilitates stable reward improvement, effectively optimizing complex multi-step decisions involving code generation and tool use. Section Summary. In this section, we describe how the Lightning client captures data without modifying existing agent code through automatic instrumentation and a lightweight tracing mechanism. We also highlight the client's robust error handling, automatic intermediate rewarding to enhance learning, and scalable environment and reward services, all of which contribute to improved performance in various tasks, including a complex text-to-SQL scenario. Section: Retrieval Augmented Generation via OpenAI Agents SDK. In this section, we discuss retrieval augmented generation using the OpenAI Agents SDK. Our focus is on a typical retrieval augmented generation task. Given a question and a database of documents, we first create a natural language query to find relevant documents using a retriever tool. We utilize the Musique dataset, which is a challenging benchmark for multi-hop question answering that encourages true compositional reasoning. Unlike previous benchmarks that can be solved with simple shortcuts, Musique is designed with a bottom-up approach, linking single-hop questions so that each reasoning step relies on the previous one. To simulate a real-world search environment, we use the entire Wikipedia as our database, which contains 21 million documents. We generate embeddings with the BGE model and use cosine similarity for our retrieval tool. The multi-hop questions and the vast database present significant challenges for our agents. We employ the LLaMA 3.2 to 3B instruct model as our base. The agent operates using the OpenAI Agents SDK, following a workflow that is simpler than the previous text-to-SQL task. The policy model first generates a query and then decides whether to refine it or provide an answer based on the retrieved documents. We use a single LLM for this process, avoiding a multi-agent setup, which means we provide one instruction that encompasses all tasks for the LLM. Unlike the SQL task, our queries are in free text, making the retrieval and reasoning steps more flexible. This task assesses the agent's ability to create effective retrieval queries with meaningful semantics and to reason over the retrieved text. During training, we use a reward system that combines a format score and a correctness score. The format score is 1 if the LLM outputs in a specific format, with content enclosed by designated tokens. The correctness score is calculated as the word-level F1 score comparing the predicted answer to the correct answer. We combine these scores to evaluate performance. Our results show that Agent Lightning consistently improves performance on this challenging task, highlighting its effectiveness in complex RAG scenarios. Next, we address a math-focused question-answering task that tests the agent's ability to use tools, specifically a calculator, to solve arithmetic and symbolic problems. We use the CalcX dataset, which includes a variety of math problems that require reasoning and accurate computation. By modifying existing math datasets, CalcX emphasizes the integration of external tools into reasoning workflows, making it ideal for testing tool-augmented agents. We again use the LLaMA 3.2 to 3B instruct model. The agent follows a straightforward yet tool-intensive workflow. Given a natural language math question, the agent must determine when and how to use the calculator tool to compute intermediate values before arriving at the final answer. This process is managed by a single LLM, which generates tool calls, interprets the outputs, and formulates the final answer. The agent must understand the structure of math problems, issue correct tool calls, and integrate the outputs into its reasoning. The final reward is based on whether the agent answers correctly, and we evaluate performance through answer accuracy on the test set. Our findings indicate that Agent Lightning consistently enhances performance during training, demonstrating its effectiveness in settings that require precise tool usage and reasoning. Finally, we explore recent advancements in multi-turn reinforcement learning for large language models. With the growth of reinforcement learning and the availability of open-source training frameworks, there is a rising interest in applying these frameworks to more complex agent training scenarios. Recent studies have investigated reinforcement learning in multi-turn, interactive environments. These methods often concatenate agent turns into a long sequence and apply specific masks for optimization. Instead, we utilize our Markov decision process formulation, unified data interface, and credit assignment module to organize data into individual transitions, which offers several advantages in capturing the complex interactions typical of real-world agents. Our transition-based modeling supports various agent architectures and workflows, including multi-agent setups, bridging the gap between training and deployment. This flexibility ensures that reinforcement learning optimization aligns with the dynamic nature of real-world agents. In contrast, concatenation methods are limited to simpler agents and struggle with more complex patterns. Additionally, organizing data as transitions helps manage the issue of accumulating context length, which can exceed input limits or increase computational demands. By treating each transition as a single sample, we alleviate the lengthening sequences caused by multiple turns. Our framework also removes the need for custom masking strategies, as only the current LLM input is included in the training sample. This contrasts with concatenation methods, which require specific masking for inputs and attention mechanisms, complicating implementation and debugging. Lastly, our transition-based approach opens the door for advanced reinforcement learning algorithms, such as hierarchical reinforcement learning, which provide better credit assignment mechanisms. This flexibility allows us to develop innovative reinforcement learning methods tailored to complex agent scenarios. Section Summary. In this section, we describe our implementation of Retrieval Augmented Generation, RAG, using the OpenAI Agents SDK, where an agent generates queries to retrieve documents from a large database, Wikipedia, for multi-hop question answering, leveraging the Musique dataset to enhance reasoning capabilities. We also discuss a math-focused QA task that integrates tool usage for solving problems, highlighting the effectiveness of our approach in improving agent performance through a transition-based reinforcement learning framework that accommodates complex interactions and reduces context length issues. Section: Large-Scale RL Training Systems for LLMs. In this section, we discuss the advancements in reinforcement learning, RL, for large language models, LLMs, which have been propelled by stable training systems like Vural, OpenRLHF, TRL, Roll, and Ariel. These systems mainly target efficient training in single-turn scenarios but often require developers to rebuild agents within the training framework. This necessity arises because existing RL frameworks need to understand the agent's execution logic to organize training data correctly, such as the order of data concatenation and where to apply masks. Consequently, agents must be closely tied to the training framework, which is challenging due to the variety of agent development ecosystems. In practice, real-world agents are highly customizable and can be created using different frameworks, like the OpenAI Agents SDK, or even built from scratch with LLM SDKs. Transitioning these agents to current RL frameworks usually demands manual adjustments to align with the framework's requirements, making the process labor-intensive, prone to errors, and hard to scale. Additionally, this migration often requires specialized knowledge of RL training frameworks, which can be a significant hurdle for many developers. The tight coupling of agents and RL training also complicates the process, as agents may have complex dependencies on various servers, tools, and APIs, adding overhead and detracting from the core RL objectives. Our framework stands out by completely decoupling RL training from agents, removing the need to write data collection logic within the RL engine and minimizing code changes on the agent side. This allows us to integrate seamlessly with various agents, regardless of their development framework. Our model also supports integration with a wide range of RL training frameworks, enhancing flexibility and scalability. We also explore multi-turn RL, which has gained attention in the RL community through works like Archer and WebShop. These studies typically involve agents interacting with environments over multiple turns but often use smaller policy models, making it difficult to apply their implementations to large-scale models. Since the success of RL methods in DeepSeek R1, there has been increased interest in applying RL to specific scenarios like retrieval augmented generation, RAG, and coding. For instance, Search R1 and R1 Searcher use RL to improve query generation and search capabilities, while Deep SWE employs multi-turn interactions to teach LLMs coding skills. However, many of these approaches focus on specific tasks and predefined workflows, rather than general-purpose agent training. In contrast, our method is not limited to specific tasks. We offer a unified approach for any AI agent, connecting AI agents with RL training methods. Moreover, our modeling framework supports various optimization methods beyond RL, such as automatic prompt optimization. We emphasize focusing on key components for agent optimization, introducing the concept of component of interest, COI, to identify components in the execution trace that are subject to optimization. For example, we can treat prompt template rendering as a tool call, allowing Agent Lightning to facilitate prompt optimization. This unified data structure supports comprehensive optimization and analysis of agent behaviors, and expanding support for more optimization methods is part of our future development plans. Finally, we recognize that developing more efficient RL algorithms is crucial for optimizing models in complex agent scenarios. This includes addressing challenges like long-horizon credit assignment and exploration algorithms. Our Agent Lightning framework organizes data in terms of transitions, making it easier to integrate additional algorithms. Section Summary. In this section, we discuss the advancements in reinforcement learning (RL) systems for large language models (LLMs), highlighting our framework's unique ability to decouple RL training from agent implementation, thus facilitating seamless integration with diverse agent ecosystems. We also explore the application of RL in specific scenarios, the introduction of optimization methods beyond RL, and the need for improved RL algorithms to enhance model performance in complex agent interactions. Section: Advancements in RL System Infrastructure for Agents. In this section, we discuss the ongoing advancements in the infrastructure that supports reinforcement learning (RL) for large language models (LLMs). This evolution offers us significant opportunities to collaborate with agent-based RL frameworks like Agent Lightning. One promising approach is to break down the system components further, specifically by separating the trainer, the inference engine, and the agent workflows. This separation can help us overcome the rollout bottleneck and improve scalability in large-scale RL training. By exploring these architectural enhancements, we can create more efficient and adaptable RL processes. Furthermore, optimizing for long-term tasks will benefit from coordinated improvements in both RL algorithms and system design, allowing us to train complex agents more effectively.